Ksenia Chernysh from Heriot-Watt, speaking about controlling differential generation to minimize forecast errors.
Hello, I'm Ksenia Chernysh from Heriot-Watt University. I'm a PhD student there, and this talk is based on my joint work with my supervisors, Sergey Foss and James Cruz. So this is the most basic scheme of energy supply. So there is some demand and it must be met using some suppliers. In this work I consider only three types of supply. So these are renewable sources, conventional sources, and imported power. This is made just for simplification. So there are main features of these sources. As we all know, renewable power is really hard to predict. Conventional power plants, they require some time to ramp up and down, so we have ramp constraints, and imported power is quite expensive, and we want to avoid purchasing this imported power. Instead of the previous picture, we will look at this picture. So net demand, as James mentioned already, this is total demand minus wind power. So there is a system operator, and there is some prediction. And this system operator, it covers already predicted energy, but there are some errors. And our task is to deal with these errors. So we have some conventional supply, and we have imported power. And we need to deal with the errors from wind prediction to minimize total cost using only these two types of power supply. This is a picture. James already showed it to you. So this is actual wind prediction data thanks to Andrew Richards, who gave it to us. And this is this is errors in 6-hour wind prediction for year-and-a-half period. As one can see, there are some big positive errors, there are negative errors, and what does it mean? Big positive error, this means block out. As we all know, this is really bad, and we need to deal somehow with this. If it's negative, don't worry, we have enough power, we can maintain our system. Okay, there are some natural questions that arises after the previous picture. So, for example, if we run some additional conventional power plants, maybe we can reduce the amount of money that we spend at these blackouts periods. Yes, at this. Here is another picture. So this is basically the same picture, but there are only errors which are bigger than some level. So only bigger errors are here, and small errors are removed. As we heard in Jean-Yves' talk, small errors, they may be covered by some storages, local storages, and they work on it. So we care only about blockout periods, these periods then we have shortage of power supply, and we want to provide some additional conventional supply in order to avoid purchasing of additional imported power and these blackout periods. We are trying to model the previous picture with these shortfalls. How we are trying to do it? For example, we can take the most simple thing that comes to our mind. This is that at every time ti, there is a shortfall, and these shortfalls, they are, of course, random variables, and they are all identically independently distributed. And here is this picture. Also, we may try to model it like the errors, they happen at some periodic time, and this is this picture. And more generally, we consider these scenarios, and these things, they are random variables which are the actual sizes of these shortages, and these are times between their arrivals. So we assume that these pairs, just for simplifications, are IID or they form Markov chain, but this will be said more precisely in the following slides. So this is the basic ideas of what we are doing. Here are some notations. So as I said before, our main goal is to define what function kt. This means the amount of power produced from additional conventional power plants, and this is kt. U and B, these are RAM constraints, and this is very essential because there are RAM constraints. Ti's, these are time moments when our shortfalls happen. And this, at this moment of shortfall, there is an error in wind prediction, which is a random variable epsilon I, and we know something about epsilon I. And tau, and these are inter-arrival times. Just for simplifications, we assume that costs for conventional and imported power are constant. This is in general not true at all. This is totally false. But to start with, we assume that there is some C1, which is cost for conventional generation. This is smaller than C2, and that's why we are trying to avoid purchasing from abroad. For period from 0 to t, we pay something for maintaining these conventional suppliers at level kt, and with evidence, this integral that is written here. So C1 is a cost for 1 unit of power, and kt is a level at time t. And if there is a shortfall of energy, and there is an error epsilon, we pay additional cost. So if kt is less than epsilon, we pay for this amount energy epsilon minus kt, and we pay C2 for every unit of energy. And if kt is bigger than epsilon, then we don't need to pay anything. I would like to say about classes of functions we are looking at. There are RAM constraints in conventional generation. That's why we suppose that these levels must satisfy these RAM constraints. We take plus here because this rate cannot be negative. And the class we are working in, this is a class of stochastic processes which satisfy almost surely this. Every realization lies, almost surely every realization lies in this class. This is where we work. This is another class. This is a class of deterministic functions. And these functions look like just piecewise linear functions which have one minimum, so they go down at the rate minus b, and then they go up at the rate u. Why do we use these functions? Actually, the minimum of our cost functional will attain at these functions. If it's really simple to understand, if your error time between your errors is deterministic, and if you know that your optimal policy goes from one point to another and it satisfies RAM constraint, you can find another policy from this class. It just goes down and then it goes up. So there is no another need to fluctuate. That's why this class is here. This is a formal definition of the cost functional. I already told you why this term is here and why this one term is here. So this is the cost for shortfall moments. This is the cost for just maintaining the system at rate kt. This is a cost functional for deterministic interarrival times. Basically, it will be the same in case when interarrival times will be random. What do we have here? Why do we have this expectation here? Because we want this k, in general, we want it to be a stochastic process. That's why this expectation is here. And this is expectation with respect to this k and with respect to distribution of this random variable. The thing we are looking at, this is infinite time cost functional. So this is average of how much money do we spend to avoid these blackouts. Here is the main result for deterministic interarrival times. So what is written here? This is a theorem about existence of the optimal policy in case then interarrival times are just deterministic and equal to some constant, and when our shortfalls are IID and we know their probability distribution function. The main result here, what is written, that the optimal policy is also periodic, and there is some level A, and it goes from level A down, then it goes up to level A again, and at time periods IT, it will be again at A. Even more, we can find this A as a solution of this simple equation. Yes, this is how optimal policy in this simple case look like. Yeah, just two cases how to open this mean term here. If it's A over B U is less than T, then our policy goes down. It stays for some time at 0 level and then goes up. Otherwise, it has no time to go down till 0. It goes down and then it just goes up without 0. So this was deterministic case for very simple. So identical interarrival times and IID random variables for shortfalls here. Currently, I work on generalization of this result for another deterministic structure, like periodic interarrival times, but there is more machinery in it. So this is a nice proof. After the idea, there is just like 5 lines to be done. And if you want to generalize it to other cases, I need to spend much more time, and after I will present these results. Here is the key idea of the proof. What is our cost functional? Cost functional, this is just we pay for the area beneath the plot, and we pay for one shortfall. My idea is that instead of this, we need to pay something in the beginning of the period, something in the end, and we pay for area. here, what is the reason? So we will pay almost the same amount of money, but we will reweight it. So in the beginning, we will pay P over this shortfall. In the end, we will pay Q, and this is the same. And it turns out that we may find the most optimal function for this with some good P. And this will be a part of the most optimal policy for total infinite time cost function. And yes. This is this main lemma for the theorem. So if you reweight the functional, then the most optimal policy for this functional will be a part of the most optimal policy for infinite time closed functional. Yes. Now we turn to a case of Poisson process. So we suppose that arrivals of shortfalls, they form a Poisson process on a real line. Let's suppose this is a Poisson process with rate lambda. We define infinite time cost functional. So there are some ways to define infinite time cost functional, but I use the same because it's simpler. One may think, what is the Poisson process and how should our optimal policy behave? For example, we know that optimal rate at this moment is kT, and we are staying here and having this kT. For example, there was no shortfall at this moment. We know that there is memorylessness of Poisson process. So we are now not better than we were before. Yes, we have no additional information about when this shortfall will arrive. So the simple idea that this level where we stay should rest the same. Because if, for example, we would have a distribution of this inter-arrival time, like we would know that this is 2 point. So either shortfall happens in 2 hours or in 5 hours. And we already know that there were 3 hours passed, and so now we know when exactly it will happen. But the picture with Poisson process is just different. If there was no shortfall, then we know nothing new. We still staying there we were. And yes, this is the theorem. So the most optimal policy for case of Poisson process, this is just a constant function, and we need to stay at this rate. Yes. We can notice that this rate is determined by lambda, 2 coasts, and that's it. So if we take different distribution functions for error process, but with fixed value, when the level will be the same. And even if we mix these errors with accordance, for example, to some Markov chain, or you can make it even more general, there still will be the same result. So we still will stay at the same level. And the last thing I want to say that what are we trying to do now? We are taking some generalization of Poisson process. So we wait for exponential time with rate lambda when error is happening. After we wait for exponential time with different parameter. And again, there is error. After again lambda, after again mu. And for example, this lambda and mu have different optimal levels. Like this k bar. They have different levels. And our conjecture is that constant policy is not anymore optimal. So there will be some fluctuations between these two bounds, because this is very simple to realize that this policy should lie between these bounds. But it's not that simple to prove how it should lie and find out even how it looks. Yes. Yeah. Thank you for your attention.
Okay, so we have a bit of time for any questions or comments.
On the sort of the occurrence time of the errors and the correlation between when an error occurs and when the next error occurs, it seems to me that I mean, you're starting from some very simplified situations, which is understandable. But I mean, there are some situations where the forecasts are more reliable than others, and that's known to some extent. It's contained within the forecast information that's given. So somehow that should tell you something about the structure of the errors that are going to be coming, or the likelihood of the errors in terms of their magnitude as they're going to be coming. It feels like there's a lot more that could be teased out of what that error structure is and your distribution of your errors going into your model. And in terms of the physical size of storms, the forecasting interval, the seriality of storms, it's known that many storms they tend to follow each other, they tend to cluster. But also in terms of the predictability, I think there's a lot more that could be explored there. So are you intending to look at this in the context of operational forecasting systems, or is this going to stay at an idealized level?
No. I hope we will do something less ideal. Yes, but for now that's it. But we will add some dependence between inter-arrival times and between levels of shortfalls. It will be added. So there will be this dependence and this correlation.
I think it was mentioned that when we speak about regenerative structure, we might think about long-term time regeneration. So you may have a mixing conditions. So we may forget some dependence. Yes. So, but within small time interval, there may be. Yes, there may be many errors, and they form some structure and they depend on each other. So it's essentially it's within the model, but we start from simple to complex.
Yeah.
Thank you.
Have you thought about the non-homogeneous Poisson process? At least you could give a little bit more kind of timing information between the.
Could you say it again?
So instead of thinking about the homogeneous Poisson process, you have a constant failure rate between the rivals. You could have at least add one more timing factors to it. So
we will generalize it in short term.
So you could have a threshold structure for the optimal policy.
Yeah. I hope I will manage to do it.
No, you cannot have threshold structure because you have ramps. You cannot jump from one level to another. So it's
I talk about the timing between the two points.
Upper and lower bounds.
Just to follow on from what everyone else has said here, if we consider the weather forecast that's coming along, the weather forecast is giving us some information about how much belief we have in the forecast we're getting and what sort of levels of error we might expect to get. So what we're getting from the forecast is an estimate of what the rate is, lambda, for your Poisson process, and what the distribution of the errors is. And you could, in a very simplistic way, just say, well, while we got this weather system, lambda and t are this, so this is the right policy for this period of time. But when it changes into the new regime, we've just got a new value of lambda and a new distribution epsilon, and that will tell us what to do in that time. And what I'd be interested in knowing is if we assume that as a great simplification, that the weather forecast was accurate about when the regimes changed, is it the case that you should just pursue one policy for the whole of that regime, and then when it changes, the new policy in that regime, or is there something that happens in the transition period,
There should be
which
something in
gives
transition
you,
period.
and what is that?
Yeah, it is the question. Because of RAM constraints, we cannot move
Yeah. So you could
immediately from one policy to other.
You could have deterministic changes between policy, and you would also know what the distribution epsilon and the new lambda I would be in the new regime, and then work out what to do in the changing period.
Can I make a comment on that? I would personally feel that the regime approach would be a bit of an awkward step in that direction. The reason being, there's a lot of the information on how forecastable the situation is contained within the forecast and the forecast spread when you have one of these ensemble forecasts. And I think if you then try to clump that into a regime, you're introducing some sort of stepping there that isn't there in reality. So it almost feels like you want to be a bit more continuous in your approach and make your policies sufficiently flexible so that your choice of policy and the shape of your policy evolves depending on the shape of the uncertainty in the meteorological forecast. So it sort of needs to be a more continuous relationship rather than discrete states, would be my feel on that.
So I see a kind of quite strong connection of this kind of a thinking process to a totally different area. It's called maintenance optimization. So basically you have a machine you're running, and in the old days you only have failure data. So it's very much discrete with very limited data. And then what happens, you have, as time goes, as the technology evolves, you have a lot of monitoring data. So you have a lot of almost like the weather forecast data become available in addition to the failure data. So in the old days, what they did, when they don't have data, they assume this kind of non-homogeneous Poisson process. That's why I'm pointing out, to try to somehow capture some information simply from the failure data, and in terms of size, in terms of timing. But now you have all this additional information outside this point process. Then you could potentially do much more, however, mathematically become much more intractable. So still you have to have all this kind of trade-off between modeling and optimization. But I think it's at least a very good starting point.
Okay, so let's thank the speaker again.